Now let's look at some actual examples of implicit differentiation. And to verify that we're obtaining the correct answer, for each example we'll plot a graph of the original implicit equation with a concurrent plot of the tangent line to the graph at a particular point, and we'll obtain the equation for the tangent line using the implicit derivative of the original equation. So to start, let's look at something slightly more complex than the circle, but not by much. Let's look at the ellipse that we looked at earlier. So here we have x squared over 9 plus y squared over 4 is equal to 1. And our task is to find the tangent line at the point 1.5, so 3 over 2, comma, square root of 3. So to see that this works, let's plug in the point 3/2, comma, root 3 into this equation to see if it's satisfied. So 3/2 squared becomes 9 over 4. 9 over 4 over 9 is 1/4. Square root of 3 squared becomes 3, so 1/4 plus 3/4 equals 1. So this is indeed a point on this ellipse. So let's plot the ellipse just to see what it looks like. Again, x squared over 9 plus y squared over 4 is equal to 1. X goes from -3 to 3. Let's say y goes from -3 to 3. So we get an ellipse like this. And so next, let's take the derivative of this equation using implicit differentiation, compute the derivative, evaluate the derivative at this particular point, and then come up with an equation for the tangent line to this graph at this point 3/2, so that's 1.5, so it's this point right up here. So the next step is to differentiate implicitly. So differentiating with respect to x, well, the first term only involves an x, so it's simple. X squared becomes 2x, so 2x over 9 plus. Next term involves y. So we think of y as a secret function of x. So think of this as y of x squared. So it's 2y of x to the 1 times the derivative of the inside, so times dy dx. So in other words, we differentiate with respect to y, 2y over 4, and then multiply by the derivative of y with respect to x. And the derivative of 1 is just 0. So 2 over 4 becomes 1 over 2. Simplify that. So upon differentiating implicitly, we obtain 2x over 9 plus y halves dy dx is equal to 0. This can easily be solved to obtain dy dx. So this goes to the other side. So it's minus 2x over 9. Then we're going to divide by the 2 over y. So the 2 comes up here, the y goes down here. So we get minus 4x over 9y. So in particular, the derivative evaluated at the point 3/2, comma, root 3, so we can write this as dy dx evaluated at 3/2, comma, root 3 is going to be minus 4 times 3 over 2 divided by root 3 for 9, so 9 square root of 3. The 3 over 3, there's 2 factors of 3 in the 9, so 3/9 is 1/3. So I'm going to next simplify this. 1/3. 4 over 2 is just 2. So we get minus 2 divided by 3 root 3. So this is the slope of the tangent line at the point up here. So pretty cool. With a couple simple steps, we have the derivative. To find the tangent line, we are going to again use the point slope formula, which is y minus y naught is equal to m times x minus x naught. So here, y minus square root of 3 is going to be the slope minus 2 over 3 root 3 times x minus x naught 3/2. So this becomes y is equal to root 3 minus 2x over 3 root 3 minus negative becomes plus, 3's cancel, 2's cancels, so plus 1 over root 3. right? 2's cancel out, 3's cancel out, minus minus, 1 over root 3 here. Now root 3 plus 1 over root 3 is equal to, okay, root 3 is equal to 3 over root 3. So 3 plus 1, it's 4 over root 3 minus 2x over 3 root 3. In fact, you can even say 4 minus 2x over 3 all divided by the square root of 3 if you want. So let's add this to our plot and see what happens. So let's add comma y equals 4 minus 2 times x over 3 all divided by the square root of 3. And we see that it is indeed tangent to can't do that. Okay, so this is indeed the tangent line to the ellipse at the point 1.5 square root of 3. So pretty cool little trick. So our next task is to take a look at the following function, implicit equation. Equation is given by 4 cosine of x sine of y is equal to 1, and we want to compute the tangent line at the point pi over 3 pi over 6. So first, is the point pi over 3 pi over 6 actually on the graph of this? Well, pi over 3 is the x value, cosine of pi over 3 is 1/2, sine of pi over 6 is 1/2, so we have 4 times 1/2 times 1/2 equals 1. So that validates the fact that this is indeed on the graph of this implicit function, or this implicit equation. To see what this looks like, let's plot this implicit equation. So 4 times cosine of x times sine of y. And then for the x window, let's go minus 5 to 5. And of course, knowing how to do this just comes about by playing around with and adjusting the window size. Minus 4 to 4. Interesting. The mistake is that this needs to be an equation, equals 1. There we go, that looks better. Okay, so square root of 3, or pi over 3, pi over 6 is probably right about here somewhere, right in there. So in fact, we can zoom in a little bit more, and we can say, let's go minus 2 to 2, and then y goes from 0 to 3. But you can see that it's a nice sort of pattern. These sorts of shapes are just kind of repeated like a checkerboard. Very interesting graph. So here's a close-up of just this part of this. Okay, so now let's differentiate implicitly. So to differentiate this, we have a product of two terms. So we're going to use the product rule. So we have this times that. So we just use the product rule as normally. So it's the first times the derivative of the second. So the first term is 4 cosine of x, and then we multiply that by the derivative of sine of y. Now here we're again regarding y as a secret function of x. So it's sine of y of x. So the derivative is going to be cosine of y of x times y prime of x. So in other words, we take the derivative with respect to y and we correct by multiplying by dy dx. So the derivative of sine is cosine, so we just get cosine of y. And then we multiply by the derivative of y with respect to x times dy dx. So this is the first term. So this is the first, and then times the derivative of the second. So the derivative of sine of y turns into cosine of y times dy dx. So then we do plus the derivative, the second times the derivative of the first. Now the derivative of cosine is minus sine, so we get minus 4 sine of x sine of y. So here we have the second, so the second factor just gets carried along, times the derivative of the first factor. So the derivative of the first factor is derivative of cosine is negative sine, so it's minus 4 sine x. And then the derivative of 1 is just 0. Again, this is a linear equation now in terms of dy dx. It's something times dy dx plus something is equal to 0. So we can solve that for dy dx. So the play is this stuff moves over there, and then we divide by this. So it's 4 sine of x sine of y divided by this coefficient, 4 cosine of x cosine of y. And this all simplifies to just tangent x tangent y. So the derivative dy dx is just tangent of x times tangent of y. So therefore dy dx, the derivative evaluated at pi over 3 comma pi over 6 is going to be tangent of pi over 3 times the tangent of pi over 6. Now tangent sine over cosine. So if we recall the values of sine and cosine of these, pi over 3, sine of pi over 3 is going to be root 3 over 2 divided by cosine of pi over 3, 1 over 2. So this is going to equal root 3 from the first term. Pi over 6, sine of pi over 6 is 1/2. Cosine of pi over 6 is root 3 over 2. So we get times 1 over root 3. So basically this equation has a slope of 1 at this point, which means that the tangent line is going to be y is equal to the starting y value plus the slope, which is 1, times x minus pi over 3. Now pi over 6 minus pi over 3 is minus pi over 6, so that's x minus pi over 6. So let's now turn and plot, add to this plot, y is equal to x minus pi over 6. And there we have it. It works. So pretty cool. Here's our implicit equation, and there's a tangent line like magic, and we can do this at any point on the curve. It doesn't matter. So for our final example, let's consider an implicit equation known as the devil's curve. So this equation is given by y squared times y squared minus 4 is equal to x squared minus 5. So this is the devil's curve. So let's take a look at this. So it's y squared times y squared minus 4 is equal to x squared times x squared minus 5. And then for the setting, for the window, let's go minus 5 to 5, and then minus 3 to 3. So this is the graph of this implicit function. You can see for a given x value, we have actually 4 different y values for this portion over here. So y is not a function of x. Now we're going to compute the tangent line at this point right up here. So we should get a tangent line like that. So the point that we're looking at for the tangent line is the point tangent line 0.5 comma square root of 2 plus square root of 2.8125. And you can verify on your own that if you plug in 1/2 for x, and if you plug in the square root of 2 plus square root of 2.8125 for y, it satisfies the equation. Tangent line at this point. So before we get there, we have to differentiate implicitly. So let's rewrite this. Let's factor in the y squared. It's y to the fourth minus 4y squared is equal to x to the fourth minus 5x squared. So this is equivalent to the original equation. I just factored in the y squared and I factored in the x squared. Now we can differentiate implicitly. So to differentiate this, we treat y as a secret function of x. So y to the fourth is basically y of x to the fourth. So the chain rule comes into effect. 4y of x cubed times the derivative of the inside. So this becomes 4y cubed times dy dx. Similarly, we have minus 4y squared, the derivative with respect to y. The 2 comes down, we get 8y, and then we have to multiply by dy dx. So this is the derivative of 4y squared with respect to y times dy dx. That's equal to 4x cubed minus 10x. So the x's we differentiate as normal. Y's we differentiate as normal, and then we throw in a factor of dy dx. Solving this for dy dx, we get 4x cubed minus 10x over 4y cubed minus 8y. Right, because there's a common factor of dy dx here, so I can factor that out of the left-hand side, leaving 4y cubed minus 8y in parentheses, all times dy dx, and then we divide by 4y cubed minus 8y. And both the numerator and denominator have a factor of 2, so let's simplify this. 2x cubed minus 5x over 2y cubed minus 4y. And then we can plug in 0.5 for x and this thing for y, which I dare not write an analytical expression, I'll just type this in. So 1/2 cubed times 2 minus 5 times 1/2 is negative 2.25 in the numerator. I'll store that in memory. And then let's also store the y value. 2 plus 2.8125 root equals this square root. So the y value is approximately, this value up here is approximately 1.917563815. Store that. Now that cubed times 2 minus 4 times that is equal to 6. So the denominator here is going to be 6.4317 approximately. So this ratio gives me a dy dx of approximately negative 0.349829501. And then our equation is going to be y0 plus the slope x minus x0, point slope form. So let's actually store y0 in for. So y0 was the square root of 2 plus square root 2.8125. Okay. And then the slope, so we'll say m is equal, we'll set this equal to 2 times 0.5 cubed. 0.5 times 5 is minus 2.5 divided by 2 times y0 cubed minus 4 times y0. So there's the slope that I came up with. Okay, so then now that we have these stored, our equation is y equals y0 plus the slope times x minus x0, which is 0.5. And there we have it. Plot color red. So there's the tangent line to the devil's curve at that point right there. Pretty cool. And then there's the tangent line up there. So we saw some pretty neat examples here, and you can explore others on your own.